All right, so let's jump right in. All right, so the perspective that we're coming at this today that I want to keep in mind as we go through the whole presentation is that data, when we analyze data, we often run across really large scale, really large, big data that is difficult to store and compute with. So those are specific challenges that come with data, and there are many different ways to approach dealing with those challenges. The one that we're going to focus on today is just exploiting any underlying structure that this data might have. So some of the examples of this structure could be low rank, multidimensional, could be sparse. We've talked a lot about sparse structured data already. I'm going to talk a little more about that today. And then, so exploiting this underlying structure allows us to address the difficulties in storing and computing with data, but we can also increase our efficiency by additionally employing randomization. So those are the two things that we're going to talk about in all of the algorithms I'm going to present today. All right, so overall here what we're going to do, I'm going to go over randomization in matrix land, then I'm going to talk about tensors and some tensor operations and decompositions in general before going into essentially randomized algorithms for Tucker decompositions baseline, going to analyze some of those, and then we're going to improve them in various ways. So that's just the overarching view that we have for today. All right, so jumping right into randomization, the main problem we are looking to solve with randomization is low rank matrix or tensor approximations. This is by no means the only problem you can solve with randomization in numerical linear algebra, but it's the one I'll be focusing on. So example applications for this, anything that Joseph talked about already this morning, where dimension reduction is useful. So PCA, subset selection, clustering, classification, things like that. So these are some example applications that I've worked on, system identification, approximating kernel interactions using tensors and structure. Okay. So the main challenges that we can address with randomization is that massive data I was talking about. And additionally, we may also need to use distributed systems with some of this massive data if it's just too large to store locally, and really computationally expensive problems. So the benefits of randomization is that it's provably accurate. We can prove in the average case that we're not losing too much accuracy by doing this randomization. And in average case and the long-term behavior, I will show you bounds today of both types. And it makes these problems more computationally feasible. Okay, so the main idea of this randomization for low rank approximations, this is just in matrix land for right now. So there's three main steps, and I'm using language from this Chihaki group survey for randomized Tucker algorithms. So the three main steps to this, the first would be dimension reduction. So we've already talked about a lot this morning, but random projection is the method that I'm going to be using for dimension reduction. You can also sample columns or things like that, but I'm going to focus on random projection for the low rank approximations. Okay, so essentially what that does is it takes this matrix and it makes it smaller and more easy to work with while trying to maintain an accurate representation of the data to begin with. All right, once we have that dimension reduction, we can do a deterministic computation. That's step 2 over here. And so that can be a QR or an SVD. The picture I've shown here is an SVD. And once you have that, you may or may not need to recover the low rank approximation of the original data. So if you notice, the left singular vectors here are not the correct size for this original matrix. And so if you are looking for approximate singular vectors, then this is not what you need. So you would need to project these back into the original space, and that is the step 3. But it's not always needed because maybe you don't need the left singular vectors, maybe you just need singular values. And you've already got those here, don't need to worry about it. So additional steps that you can avoid if you don't need it. Okay, so I'm going to present 2 different methods for doing this, which are going to be the randomized range finder. That's going to be one more of this style where we don't necessarily have the correct space always. And then we have a randomized SVD, which will be more in this style. Okay, so randomized range finder, what it does is it takes a matrix and it gives you an approximation Q that approximates the range of your matrix X. So the way that we do this is we have a matrix X, we can draw a random matrix omega. This matrix can be of any distribution you like, Gaussian, Rademacher. I'm going to use Gaussian and SRHT, which is subsampled randomized Hadamard transforms. Those are the ones I'm going to be using. So you draw this matrix, you form the sketch Y, multiplying it together. And that means that Y is then made up of linear combinations of the columns of X, which when we do that, we can take a thin QR of that sketch Y and get a matrix Q that approximates the range of our X. So important thing to notice here is that this Q that we're getting is an approximation for the range, but it is rank R plus P. So it's going to have R plus P columns. So if you need a rank R, like target rank R approximation, this is not going to do it for you. You got to rank R plus P. So you got to be more careful if you definitely need like an approximation of a certain rank. Which leads us to randomized SVD. So what we can do with this, essentially we take the randomized rangefinder and then we do some post-processing. So starting again with that matrix X, we do a randomized rangefinder to get a matrix Q. We then form this B matrix, which is Q transpose X, and take it a truncated SVD of this B matrix. So the reason we do that is because if we just wanted to take an SVD of X, that is could be quite large. B is going to be smaller. It's going to be particularly useful in the case where X is tall and skinny. The case where I'm going to be using it is where X is really short and very, very wide. And so B is going to be smaller than X, but not like as substantial as it would be if we were dealing with tall and skinny matrices. Okay, so once we do that, then we have this U hat and sigma V transpose as our approximation to an SVD. And if we need our left singular vectors, we would project that back into the correct space by multiplying it by Q. Okay, so this gives us an approximation for the SVD. So just some analysis, how well does this work? So randomized rangefinder, I'm going to say is RRF, that's going to show up several times. The expected bound, about to leave one over there, the expected error, squared error in our approximation from the randomized rangefinder with respect to our random matrix omega is going to be bounded above by, this is the best case error scenario that we would get from doing an actual truncated SVD. These are the discarded singular values. So we have those multiplied by this factor 1 plus R over P minus 1. So notice that P, which I haven't really talked so much about, is an oversampling parameter. And the bigger P is, the better our error is going to be. So what P is essentially doing is taking extra columns of our matrix so that we are guaranteed to get the right columns is essentially what we're trying to do, and trying to increase the probability that we get an accurate representation of our matrix. Okay, so we don't want to take it too big. The best case for P, there's really good theoretical guarantees for like P equals 20 specifically, but in practice, most of the time it's like P equals 5. You could take it even smaller. I've done P equals 2 and it's enough. So it depends on what you need. All right, so this is for randomized rangefinder. Then for randomized SVD, we have essentially another layer in there. So this seems backwards in that the approximation you get from the randomized SVD should be better than the approximation you get from randomized rangefinder. But the thing to remember here is that our randomized rangefinder is actually rank R plus P. So we're getting a higher rank approximation to our matrix, which is going to be better. So it's going to have lower error than our rank R approximation from our randomized SVD. So what this bound is saying is that essentially truncating down to rank R is going to increase our error, but it's going to leave us with the same worst case error bound of those discarded singular values times that small factor. So that's nice to have. Then for computational complexity, the randomized rangefinder and the randomized SVD both have the same worst dominant cost asymptotically, but randomized SVD, we're doing more operations of that dominant cost essentially. So we have more lower order terms for randomized SVD, even though they have the same higher order complexity. So we can keep in mind that with randomized SVD, there are going to be extra costs. Okay. So there have been many, many improvements to randomized SVD over the years. And so I'm going to talk about a few of them here. The one that I've shown is just like the vanilla randomized SVD, and you can improve on this significantly by doing a number of things. So this first example, subspace iterations, what this does is it is going to increase the accuracy of our approximation by doing these power iterations of XX transpose times the sketch when we form that sketch Y. So that's going to increase our accuracy, but in the cases of really large data, it's going to also make it significantly slower, and it's going to increase the number of passes that we need through the data, which we may not want to do, especially if we're working in parallel. So then there's also an adaptive randomized SVD. So one of the key problems that Joseph talked about this morning is how to choose that rank. So, and all of the algorithms I'm going to show you today actually take the target rank as an input, but it's not necessarily the best thing to do because you may not know ahead of time with your data what the target rank should be. You may have a guess, but you may not. And so what adaptive randomized algorithms do is it instead takes an error tolerance that you want. So say you want an approximation that's accurate to 10 to the minus 2, you give that in, and it gives you an approximation that satisfies that error tolerance. We actually, so even though I'm going to show you ones that take the target rank as input, we actually have adaptive versions for all but one of the algorithms that I'm going to show you today. And so this is better in many practical applications, but it can get a little more complicated. Okay, and then there's this, there's other like computational benefits you can do, such as like RSVD pack, where instead of doing a truncated SVD of that matrix B, you can use an eigenvalue decomposition instead, or use a QR of the B, and that would increase your, decrease your computational complexity, and yet also maintain a similar amount of accuracy. So this one could be used in particular to speed up our algorithms. Most time, just to keep things simple today, I'm going to stick with the vanilla randomized SVD that I've shown you, but these are improvements that we could make. Okay, so I'm going to show you some numerical examples now and include the subspace iterations just to show you what they do. All right, so I've got two different examples here. I've got a random 1000 by 1000 matrix and a 1000 by 1000 matrix that I set up to have 10 really large singular values. So here I chose target rank to be 50 and the overlaying parameter to be 5. And I'm looking at what are the singular values of these matrices, and then what happens if we compute it with the randomized SVD, and then what happens if we compute them with one or two subspace iterations. So on the left-hand side, you can see the true singular values are this blue line up here. And the randomized SVD, I mean, it's approximately the same pattern, but just in this random case, it's like not so great. But if we put subspace iterations on those, we can get closer and closer to the true singular values, and probably one or two more subspace iterations would get us right up to the singular values. But in the case where our singular values are decaying very quickly, so this is a naturally low rank matrix, all four algorithms are computing singular values that are like right on top of each other until the very end when randomized SVD doesn't do so well on the small ones. So we can see from this that, and not every situation is going to be perfect for randomization. So I'm going to try and sell you on it, but it's not going to work in every case. It's going to work really well when the singular values decay rapidly, such as in the synthetic case. One more thing with this I want to show you is just timing. So a full SVD for the random matrix takes about 0.34 seconds, and then everything else is about a factor of 10 or so less. And randomized rangefinder is the fastest by far. But I can't plot the singular values from randomized rangefinder because we don't get approximate singular values from that algorithm. Okay. Then the relative error in the matrix approximation. So for randomized rangefinder, that would be that QQ transpose X. And for randomized SVD, it's going to be the approximate SVD. So here, even though we didn't approximate the singular values particularly well, our relative error is very close to what we'd get from an SVD of that same rank. And that is nice to see. The other important thing to notice here is that in both cases, the randomized SVD and the randomized rangefinder are basically on top of each other. You can't see the randomized rangefinder underneath the red line, but it is there. And the reason for that is that, again, the randomized rangefinder, this is a rank R plus P approximation, so it's going to be better. If we were actually going to get, say we put in a target rank of like R plus P or R minus 5, and then de novo saying parameters, we could get a rank R approximation, we would have one that would be up here somewhere. So it wouldn't be quite as good. Okay, so that's my spiel on randomization for matrix land. And the takeaway that I want you to get from this is that using dimension reduction via randomization can significantly reduce computational cost of computing low rank matrix approximations. That's going to work particularly well when singular values decay rapidly. And I showed you two different methods, randomized rangefinder and randomized SVD, that have equivalent asymptotic cost, but we have to keep in mind randomized SVD has more lower order terms. Okay, so now let's move into tensor land. So why are we thinking about tensors? Many different cases, multidimensional data appears everywhere. Everywhere I look now, the data is inherently multidimensional. A lot of times it's treated as matrices, so because we have a lot of good matrix algorithms to compute approximations with, and so we want to use those. So one of the things that we're trying to improve is that to create similar accuracy, similar high-performing tensor algorithms that can do the same thing, but keep that multidimensional structure. So that's the goal that we're coming up with. So some of the applications where multidimensional data appears, I've listed here. This example right here is a hyperspectral cube. And essentially what this is doing is, so we've got an image in the front, that's this X and Y modes. And the third mode is the wavelength frequency of this, like the spectrum, essentially. And so what you're trying to do here is use that information to figure out image recognition pieces. So it's like this might be water based on the spectrum of that particular piece. So this data can get quite large. If you think about this, if you're looking at a very large picture, then the number of or very high definition number of pixels you're going to have in each mode can get quite large, which leads us to that difficulty of storing and computing with this data. So our method here, in order to efficiently compress this data, we're going to keep it in tensor form. Importantly, we're going to use tensor decompositions. I'm specifically going to talk about Tucker decompositions because it has really high compression ability. So we're able to obtain really large compression ratios using the Tucker decomposition and still maintain high accuracy. So we've heard a lot of, Sabina mentioned the CP decomposition a couple of times in her discussion, and that one's really good for interpretability. But I'd like to argue that Tucker would be really good, is good for compression. And if you want to have interpretability later, you can use the Tucker decomposition as an initial guess to your CP algorithm and actually get a better, like you can get that interpretability while having the compression benefits of Tucker. Okay, so a couple of tensor operations we're going to need here. The first is matricization. So the idea is turning a tensor into a matrix. Easy way to think about it, say you've got like a Rubik's Cube and you take your Rubik's Cube and you slice it in a bunch of pieces and lay out the slices next to each other. That's essentially what matricization is doing. So I've got an example here. So this would be a 3-mode 2x2x2 tensor laid out in slices. And what we do here is for each mode, we have a different matricization and we lay out what we call the mode J fibers. So in mode 1, those are columns. Mode 1, there's a rows. Mode 2, those columns. And then mode 3 would be, they're called tubes, but after that, they don't really have specific names. We just fibers at that point. So this 3-dimensional case, so you can see for the first matricization, we are taking the columns of these matrices. I guess this is just backwards. Columns and laying it out in a matrix. Then for mode 2, we're taking the rows of our tensor and laying those out as the columns. And for mode 3, we're taking 1, 5, which would be the tube fibers like into the screen and laying those out as our columns. So that's what matricization is. We can unfold and refold, and we're going to do that so we can use some of those really great matrix techniques and matrix analysis results while still working in tensor with tensors. Okay. The other key operation for tensors is this tensor times matrix, or a TTM. And what we're doing here is we're taking a tensor and we are multiplying it by a matrix along a mode. So in their example, this would be in mode 1. And the way this is just computed as matrix multiplication. So this is one of the examples of how we use matricization, is that we're going to take this matrix U and multiply it on the left by the unfolded version of X in that mode. So essentially you're taking the mode J fibers and you're multiplying that by the matrix. Okay. We can not just limited to one mode, we can do this in multiple modes, up to D for a D mode tensor. And essentially this would just be computed as a sequence of matrix multiplications. And the important part about this is that we can, I didn't put this on here, but what this does is when we multiply a tensor by a matrix in a specific mode, the dimension in that mode is going to become the number of columns of our matrix. So if the number of columns of our matrix is small, then that reduces the size of our tensor in that mode. So if we do this multiple times and we choose our matrices well, we can reduce the size of our tensor by doing that. So we're going to take advantage of that later. And a key property of this multi-TTM that we're going to use is if we unfold that along mode J, it takes this form here, which looks really complicated, but it's just the Jth matrix on the left, the matricized tensor here, and then the rest of the matrices, Kronecker product together in reverse order. And we're going to remember the structure because it's going to come up in several minutes. Okay, so those are some key operations. Put those together. This is the Tucker form. So it's Tucker decomposition. What it does is it takes a tensor X and it represents it as the product of a core tensor G times D factor matrices, one for each mode. So the idea here is that this would be our low rank representation because our core tensor is going to be hopefully significantly reduced from the size of our original tensor. And then we have factor matrices that can are orthonormal. So you can sort of see how this is a generalization to an SVD for matrices. So there's a couple of popular algorithms to compute this deterministically, and that would be the higher order SVD and the sequentially truncated higher order SVD. So it's going to be alphabet soup here in a little bit. But the idea of these guys is that, and this is going to be the general framework for most of the algorithms I'm going to show you today. is first, we unfold the tensor along each mode. We do a rank RSVD of that mode unfolding, take the left singular vectors, and that becomes our factor matrices. And then we form the core via TTMs with the factor matrices. So that's a general framework, and this is the higher order SVD. So there's a couple ways to change this and improve that. So the sequentially truncated higher order SVD is, instead of computing each mode independently, we're going to update the core tensor as we go along. So the idea here, we take a rank RSVD of the unfolding, save our factor matrix as those left singular vectors, and then we update the core tensor. So we're going to save the core tensor as the scaled singular vectors, and then repeat on the core tensor. So here's a visualization of what this looks like. So say we've got, this is our original tensor. We're going to process the first mode and truncate this highlighted part off. Then we take the rest of it and we process that again. So this is, eventually we're going to truncate all modes until we have a smaller core tensor at the end. So there's some benefits to this. It's going to be computationally cheaper because we're dealing with a smaller tensor each time. So this is a great way to go. But the important things to notice is that the order in which you process these modes is important. You're going to get a different approximation depending on with different processing orders. So you have to be careful in how you choose that. Okay, that's background for tensors. So now jumping into my work here. So we're starting off with randomized algorithms for Tucker decompositions in general. This is work with Arvind Saibaba and Misha Kilmer. And I'm going to talk about now algorithms and analysis. Okay, so both HOSVD and STHOSVD, the dominant cost of that algorithm is the SVD of one of the mode unfoldings. In the STHOSVD cost, it's specifically the first one you compute, because it's going to get smaller from there. But in both cases, that's the dominant cost. So if we replace that SVD with a randomized SVD, we can reduce the cost. This time it would be a dominant cost of this Q transpose X. That would be that B matrix in the randomized SVD. And that's going to reduce the cost by essentially an order of magnitude. And then we're going to have factor matrices that approximate the left singular vectors instead of being the actual singular vectors. We can improve this further by using randomized range finder. Now the dominant cost, because we're not even computing an SVD in this case, it's just the matrix multiplication with the random matrix omega. And that going to have the same cost here, but again, those lower order terms are cheaper. The only problem with this now is that our factor matrices do now just approximate the range as opposed to the actual singular vectors. So if you need the singular vectors, can't go this route. So, but our general idea here is let's replace that SVD step with something that's cheaper and use randomization to do it. All right, so that leads us to our randomized HOSVD algorithm, or randomized Tucker. And what this does, so notice that we are taking in a target rank, and that is a target rank for each mode. So you can change this up and your core tensor can be different sizes in each mode. And it's the same framework as we've seen before. So we're going to unfold the tensor along mode J, compute a randomized SVD of that unfolding. Notice it's important that we use an independent random matrix for each mode. That's going to come up in our analysis. We're going to need that. Then we form the factor matrix using the left singular vectors, which are now approximate. And then after all modes are processed, we can form the core by a multi-TTM with all of the factor matrices. Okay, so fairly straightforward. We can improve this to do the sequential version. So it's essentially, I'm not going to spend much time on this because it's basically the same thing. So each mode, you do a randomized SVD, and then you update the core. And so it's basically the same as STHOSVD with the randomized SVD in there. Okay, important things. After each mode, you have a partially truncated core, like you can see from that picture. And that leads us to say we can have partial approximations to our tensor. So if we stop after mode J, we'll have this partial approximation to our tensor, which can also be written as this if we just plug in what G is in terms of that product. So, and that comes up with our analysis, which I'll show you in just a second. Okay, so this is an error bound that we proved. And essentially what this is saying is that, and now notice that I'm taking the simple case here where I'm taking the tensor to be the same size in each mode and the target rank to be the same in each mode as well. And that's just for notational simplicity because this notation can get nasty. So just to show you here is what we've proved it for the general case. So what this is saying is the expected value of our approximation error squared with respect to all of our random matrices is bounded above by, notice we have the discarded singular vector, singular values in each mode. So we have D, those added together, times the same factor that we had from the randomized SVD. So this is actually really good because we're going to get, using tensors, D mode tensor, we're going to have this factor of D here regardless. Nothing we can do to get rid of that. But keeping it just to the amount that we're losing in randomization anyway is pretty good. Okay. Then you can also rewrite this in terms of the optimal approximation. So, and so we have the D term, and essentially that's just saying that this would be the discarded singular values is the best we can do. Okay, some other notes about this error bound. This bound is independent of the processing order. So what that means is though, even though we are going to get approximations that are different and have different errors with each processing order, the worst case error bound is going to be the same. And so that's really nice. So you don't have to worry too much. You can choose the processing order based on computational complexity instead of error. Okay. Then if we just really nice, if we choose the overslain parameter to be r+1, this simplifies really nicely to this pretty form that looks really nice. Okay. So I think I'm doing okay on time. So I will go, yeah, I will go through this. I was going to skip this if we didn't have much time, but I think we're doing okay. So I want to take you through a very brief proof summary of that algorithm because it looks really nice, but there are a lot of intricacies that go on beneath the surface. So I want to show you what some of those complexities are. So just in 3 dimensions, because again, the notation is gross, we're taking a tensor that's the same in each mode, target rank the same in each mode, and processing order 1, 2, 3, just to make our lives easier. And I'm going to use this notation up here because we're going to have the expectation with respect to several different random matrices. And I want to make our lives easier. So just using that. The other thing to keep in mind is that this G to the J are partially truncated core tensors, and the X hat to the J are going to be partial approximations after the Jth mode. Okay, so main steps to this proof. Essentially, we're going to use linearity of expectations and the independence of our random matrices. We're going to rewrite some stuff and unfold some stuff. Then we're going to bound those matrices using randomized matrix results and put back into tensor form. Okay, so first thing, we can write our approximation error using essentially the Frobenius norm and adding, subtracting some stuff. In this sum here, sorry, not the Frobenius norm, in the Pythagorean theorem is how we can write this out with an equal sign. So essentially what this is saying is that the approximation error is the same as the approximation error in between our partial approximations. So it's the sum of all of those. All right, so we can use linearity of expectations to distribute the expectation across all terms in the sum. And then notice that in this first term, the only random matrix that we have incorporated at that point is the first one in the first mode. So that's the only one that's going to affect this term. Similarly, for the second term, we're only going to use omega-1 and omega-2, but for the third term, all 3 have been incorporated. So we have to take those into account. All right, so let's look at this last term, and then we're going to deal with this one and then combine it at the end. So using the independence of our omegas, we can actually express this expectation as the expectation of an expectation. So that's because of the independence of our omegas, we can peel off this expectation with respect to omega-3. That's going to make our lives easier later. All right, so now looking at just this term, getting rid of the expectation for now, we'll come back to it. We're going to rewrite this term and unfold it. So rewriting, essentially, the way you can think about this is if you distribute this multiplication, we'll have the second approximation times I minus the second approximation times the third factor matrices, which is how we formed the third partial approximation in the first place. We just rewrote it. Now we can rewrite X hat. That's our approximation in terms of the core tensor times those factor matrices. So we have this term here, and then we can unfold it. So in the third mode, so we're going to have this matrix to the left. This is the third mode matrixization of the second partial core tensor, and then times the other factor matrices in reverse order. Okay, now that we've got that, we're going to bound this term using randomized matrix results. So the first thing we can do is keep in mind that these A matrices have orthonormal columns. So we can just pull those out with no problem. They're only going to decrease the norm. And then we're left with this part here. So this is a result from Hauke-Martinson and Trop. This is essentially just the like x minus QQ transpose x is what we're doing here. So you can see this is the 1 plus r over p minus 1 times the discarded singular values of our matrix. But this is tricky part. So our matrix here is the partial core, and the partial core is a random quantity. So this is not enough. We can't stop here because we want this to be a deterministic value. So what we have to do is use some trickiness, and I can show you more detail about this later, but essentially we're going to use properties of GG transpose, in fact that is semi-positive, symmetric, positive, semi-definite, use some properties of the eigenvalues of those guys to relate that to the eigenvalues of XX transpose. So that's what we're doing, and I can show you more details about that if you would like. So using that trickiness, we can relate this to the singular values of our X, which is now not a random quantity, and that's what we wanted. Okay, so because of that, this is now a deterministic quantity, which means if we're taking the expectation of that, it's just the quantity because it's a deterministic value. Okay, so we've got that there. Summarize, here's what we've done so far. We've taken that last term in the sum, the expectation with respect to all 3 random variables, matrices, and bounded above by this term here. From there, it's just a combining into the sum. So we can do that for each term in the sum, and we can bound it above by what we see here for 3 dimensions, and the same as what I showed you in the theorem. So there's a lot of intricacies there. It's more complicated because we have to deal with those random quantities in the partial cores. So that's why I wanted to show you that. Okay, oh, right, and you can take square roots if you wanted just the expected error. Okay, so let's look at some numerical results now. So I've got a tensor that we can call, I've heard called the Cauchy tensor or the Hilbert tensor, and essentially we're forming the this entry-wise by 1 over all the sum of all of the indices. That's each entry. So this guy is pretty dense. It's 5-way, which gets large very quickly. My laptop only can handle about 35-way before it starts saying that that's too much. So this is fairly large for local. So I'm taking an oversetting parameter of p equals 5 and a processing order of just 1 through d, and showing the relative error for STH to SVD and the randomized version. So what you can see is that they're very, very close as the target rank increases, almost essentially down to machine precision, where then it starts to rain off. So really, we're not losing too much accuracy with this approximation. And with runtime, we can also see that it's again about an order of magnitude from STH to SVD to the randomized version. Then, okay, how good is this error bound? So let's plot now the approximation error for STH to SVD and HOSVD, because I don't think I mentioned it's the same bound for both, compared to the error bound here. And really, this error bound is very close to the actual error that we are seeing. So this error bound does a really good job of telling us what our error is. It's not too pessimistic. Okay, takeaways from this section. So we can incorporate random matrix techniques into TensorLand in order to reduce the cost, and it provably increases the expected error only by a small factor. So there's just some, these are the 2 algorithms that I showed. Okay, so let's improve on this. So that was sort of baseline. What can we do to improve this? So this is going to be work with Gray Ballard and Zitong Li at Wake Forest University. And what we're going to talk about is essentially we're going to use Kronecker structured random matrices now and a parallel implementation in order to improve on this further. Okay, so just recall the general approach. I'm going to keep showing this to you. We unfold, randomize SVD or rank our SVD, left unit vector of the factor matrix, and we form a core. So our approach here is we're going to modify this randomized algorithm in order to speed up the SVD step. So instead, we're going to use a Kronecker product of random matrices in order to exploit some structure. And then we're going to implement this in parallel. And we're going to specifically use a new, faster parallel version of that multi-TTM operation in order to significantly lower our runtime in parallel. Okay, reminder of what the randomized rangefinder is. Let me show you how we're going to improve it. So we're going to use, instead of omega, just an n by r plus p random matrix of some distribution. We're going to form our omega as a Kronecker product of really skinny matrices. So the idea here is that thinking about if we put it in TensorLand, this x is going to be our unfolded tensor, So our unfolded tensor is going to be really, really wide, right? So it's going to be like n to the d-1 number of columns. So if we take our Kronecker product to have n rows, and essentially I'm going to call it S, and that S to the d-1 is going to be equal to r plus p. So if you think about that, it's going to be a really, really small number of columns that we're dealing with here. So these matrices are going to be very skinny. So the idea about this is that if we take this structure for our random matrix, then this is like very similar to that form of that unfolded multi-TTM. So we can actually use a multi-TTM in order to form our sketch. And that's going to be really important. Okay, so that leads us to this main algorithm. So for each mode, this is just an HOSPD. ST-HOSP is a little more complicated, so we're not going to talk about it today, but there is a version for it. So we're going to do a randomized rangefinder of the unfolding xj. But to compute the sketch, we're going to do a multi-TTM with all of those really skinny phi matrices. Then we do a thin QR of that sketch and get our factor matrix AJ that, notice it has r plus p columns. So we're going to have to deal with this later. We're not doing a randomized SVD here, which means we're getting a rank r plus p approximation. So we're going to have to deal with that. But it's going to be nicer, computationally cheaper. So once we have all of those for each mode, then we form the core using another multi-TTM in the same way. And then we have to truncate down to the target rank. So we have a rank r plus p approximation. And in order to truncate down to rank r in each mode, there are several different ways to do this. We're going to do a deterministic HOSVD on our core. So essentially what that means is we're going to have an even smaller core of rank r and more factor matrices that will then combine with our original factor matrices to get a Tucker decomposition. So that's the idea. And the reason we can do this is because we've already theoretically compressed and gotten a smaller core tensor to begin with. So we went from size n to size r plus p, which is a significant reduction if we've chosen our ranks well. And then doing a deterministic HOSVD shouldn't be that much more expensive, so it is not too bad to do. Okay, so we have, just to compare again, what we're doing here, we've got the traditional approach would be one really large matrix multiply, which was the dominant cost in our randomized rangefinder algorithm. And we're changing that to do one multi-TTM with really skinny matrices. And the idea is that we're going to create an approach for doing a multi-TTM with skinny matrices so that we can do that really optimized. Okay. So there's two different approaches that we can take, two different options. The first is to use an independent product of phis per mode. So each mode, we generate a new set of phis, and we use that for multi-TTM. Another option would be to reuse the same Kronecker factors phi. So that means we generate only d phi matrices, and then we reuse sets of them each mode. So a couple things about this. If we do it this way, we have independent products, which is nice for analysis, but we're generating and storing more random matrices. And if we reuse the same factors, even though it does make the analysis more complicated, we can reuse computations and actually implement like a dimension tree in order to make this even faster. So we're going to look at both approaches, but this is the one that will be faster. Okay, so we have a theoretical bound for this algorithm. So a couple of things, this is going to be in the form of a tail bound. And if you haven't heard of that, what that means is that this bound is going to hold with a given probability. And that's essentially all that a tail bound is. So if we've got a D-weight tensor, target rank same in each mode again, we're going to have these alpha and beta quantities that need to satisfy this inequality. So essentially that's just parameters that you can play with. Notice that alpha and beta appear both in the bound, and then beta appears in the failure probability. So you can play with that to either increase the probability that this thing holds or decrease the constant that we're multiplying by our optimal approximation. So you can do this either way. Okay, so the random matrices that we're going to use for this are SRHT. And the reason for that, which I will show you in a second. So essentially what SRHT random matrices are they these diagonal Rademacher matrices multiplied by randomly sampled columns from a Hadamard transform. The idea is that you can implement this efficiently so that when you multiply with them, you can do that optimized using a Hadamard transform. We don't actually find the need to do that because we're going to optimize the approach anyway, and it doesn't actually give us that much more benefit to do it. Okay, so some notes about this bound. We're using this SRHT random matrices because essentially you could think about Hadamard matrices, they're formed using Kronecker products of smaller size Hadamard matrices. So because of that, we can actually generalize randomized random matrix theory from using a single SRHT matrix to Kronecker products of SRHT matrices really nicely. That's why we chose those. Gaussians don't work so well because the Kronecker product of a Gaussian is not a Gaussian. So you can't use that. All right. The important thing about this bound too is that this is going to allow for an independent product of random matrices, or the option where we reuse. So we're okay even losing that independence with this bound. This can handle that, which is a really cool thing. The other thing, this bound is not quite as tight as the one I showed you for randomized STH-SVD. It's a little pessimistic, but we're hoping to improve that using some further results. And the numerical accuracy results that we're showing are very good, which I will show you in just a second. Okay, so I'm going to have two different things to show you today. We have a 500 three-way tensor with moderately decaying singular values, so our randomized approach should work pretty well. Taking a target rank of 10 in each mode, overswing parameter of 5, and S is going to be, that's the number of columns of those 5 matrices, so that's going to be 4. So compare that to 15, that's the kind of multiplication that we're doing, which would be nice. Okay, couple of things here. So I'm comparing the HOSVD versions for using an independent Kronecker product per mode, and then reusing the Kronecker product, the same factors for the whole thing. And notice that I am using SRHT random matrices for this guy, but I'm using a Gaussian random matrix for the full randomized HOSVD. And the reason for that is the way that we implemented this, like very quickly in MATLAB, we have to generate a really, really big SRHT matrix in order to do this one, and it just isn't worth it, so we're comparing to Gaussian. Okay, but for 100 trials, we can see that the relative error for each of these is basically the same, and we're plotting this against the deterministic HOSVD error. So we are getting really good accuracy with these algorithms, whether we use the same Kronecker product of matrices or we generate independent ones. So that is nice. And now just plotting the relative error versus the target rank in the same sort of case. Notice that S is going to change as we increase the target rank because it depends on R, but it's never going to be bigger than 11. And all 4 algorithms that I'm plotting here are basically getting the same accuracy. So we're really seeing good accuracy results with these randomized algorithms. Okay. All right, so now how are we parallelizing this? So the idea here is, say we have a tensor and we're going to store this on a processor grid. This is an example of a 3x2x2 processor grid. And essentially each processor is going to store a local piece of the tensor. So the idea for this is that we're going to parallelize key operations so that we can minimize both the communication and the computational cost. So there's a trade-off there that we have to play with, but that's going to be our goal. And the key operation that we're going to talk about is the multi-TTM. And the reason for that is that it shows up in multiple different places in our algorithm. So when we process all modes, we are essentially doing D multi-TTMs here, and then we're doing another TTM at the end to form our core. So there's 2 different flavors of TTM that we're doing here. So this is a multi-TTM with really, really skinny matrices, and this is a TTM with slightly larger matrices. So we have 2 different types, and it's going to turn out that there's going to be 2 different methods that work well for each type. All right, so this is the multi-TTM approach that we are proposing. So the goal is to compute a multi-TTM for some number of matrices. And there's 2 different versions, an in-sequence approach and in what we're calling an all-at-once approach. So looking at this example, this is just in 2 modes, so we can view it as a matrix. Then the multi-TTM can also be written as U transpose XV. So this is a visualization of the processor grid that a matrix is distributed across. And the highlighted part is essentially what one processor would own here. So the in-sequence approach, okay, so we're going to take U transpose, multiply that by X locally, and communicate that result across all processors. Then we're going to compute the multiply with V and then communicate that result. So that's the in-sequence approach one at a time. We're going to do an all-at-once approach, which is going to compute locally U transpose XV all at once and then communicate that result. So this generalizes really well to D dimensions. You can picture how that would work. Okay, so comparison between these 2 approaches. The in-sequence approach has fewer flops because the size of the things that you're dealing with is smaller, but it's communicating more. Whereas the all-at-once approach is going to have slightly more computation, but generally less communication. So there's going to be a trade-off in where these are useful. So the in-sequence approach is better when the matrices have more columns, and all-at-once is going to be better when the matrices have fewer columns. So that leads us to say, okay, we've got two different flavors of multi-TTM. Let's use one approach where it's useful and the other approach where that one's useful. So we're going to use in-sequence approach for forming the core, as those matrices have more columns, and we're going to use the all-at-once approach to form the sketches, as those are going to be really skinny, and we're going to reduce computation in those cases. All right, so let's look at how this works. So this is a comparison of the two multi-TTM methods with an increasing number of columns S of the matrices. So for small s's, you can think about that as our random matrices phi, and the larger S would be for our core forming. Okay, so we're looking at a four-way tensor, 250 in each mode. We're running this on 16 cores for a single multi-core server, and we're using Gaussian random matrices because I think at the time when Zitong had run this, we hadn't implemented the SRHT yet. So for an increasing number of S, you can see the trade-off. So for small s's, the all-at-once approach on the left is less, and that includes up to here is where we can see the most dramatic change, because especially in these guys, you can see that communication is significantly less in the all-at-once approach than in the in-sequence approach. But when S gets large, so in the 128, then the computations overwhelm the all-at-once approach, and so an in-sequence approach is better. So it's a trade-off of just the size of the matrices. All right, so if we incorporate those into our algorithm in the way that I've talked about, then what happens if we do the full thing? So this is a comparison to the deterministic ST-HOSVD, and we're working on implementing the randomized HOSVD with a full random matrix so we can have a better comparison with something that's closer. But there's some trickiness with that in the parallel form. So it's slightly different tensor, four-way, 256 in each mode, 32 target rank, and we're using the reuse. So we're reusing the same Kronecker factors for each mode. I'm running this on Andes from Oak Ridge. So this would be the full algorithm. You can see that the SVD step is dominating the ST-HOSVD algorithms, and we're able to significantly reduce that with essentially this the RRF portion of our randomized algorithm. So we are really seeing significant improvements to deterministic versions, and we expect with respect to randomized versions as well. All right, takeaways from this: we're able to exploit Kronecker structure and parallelization to speed up our randomized HOSVD algorithms, and we can use it on distributed systems, which is a real win. Okay, so that's all the different approaches that I've talked about. All right, last portion, we're going to improve further, essentially, and I'm going to show you a different form of a Tucker decomposition that's going to allow us to preserve structure. So this is, again, work with Arvind Saibaba and Misha Kilmer as well. Okay, so we're proposing a new form of a decomposition. So this is a structure-preserving Tucker decomposition. And notice that it's the Tucker form, but I've colored the original tensor X and the core tensor the same color. And essentially what that means is whatever structure X has, our core tensor is also going to have. So this is not the case for most algorithms for Tucker. If you have any like sparsity in X, you're going to lose it completely when you go to the core tensor. And this is we're going to have algorithms that are going to prevent that from happening. Our core is going to have sparsity if our original tensor is as well. Okay, so we've got two different algorithms to compute this, an HOSVD and an ST-HOSVD version. Okay, so the idea behind this is thinking about randomized rangefinder. We have this approximation QQ transpose X, and other decompositions take the Q and form the factor matrix. That's what I did in the last section. And then Q transpose X is going to be used to form the core. But if X is sparse, multiplying it by Q transpose is going to completely destroy the sparsity. So we want to avoid that. So what we're going to do instead is use subset selection, like strong rank filling QR. Other subset selection methods would work just as well, to obtain the selection operator P, which essentially is going to choose well-conditioned rows of Q. So that using subset selection is going to give us this approximation here. And instead of just taking Q to be our factor matrix, we'll take the entire blue section to be our factor matrix. And then notice that the part that we use to form the core is going to actually extract entries from the original matrix, the original tensor. So this is going to allow us to form a core out of entries of the tensor itself, which means that any structure that our tensor has will be in the core as well, because we're taking entries from the core from the tensor itself. Okay, so that leads us to the structure preserving sequentially truncated higher order SVD, alphabet soup. So essentially what we're doing here is this is the same format, we're just changing things slightly. So for each mode, we're going to unfold, do a randomized rangefinder to get that Q. We'll then extract rows from the unfolded core using subset selection method, strong accumulating QR. So that will form our factor matrices here, and then we'll update the core tensor by extracting entries. So this is just a visualization of how the core is formed. So we start with a full tensor, unfold along the first mode, do randomized rangefinder, extract rows, use those rows to form our secondary core, do the same thing, repeat, extract rows until we've gotten a core tensor that is made up of entries from the original tensor. Okay, so computationally, this really depends on the number of non-zeros of the core originally at each step. So it's going to be really, really cheap for sparse tensors. So the dominant costs here, this first part comes from using the strong regulating QR and the thin QR factorization used to get our factor matrices. And the second part is the product of the unfolded tensor with our random matrix. And this is the part that's going to be much cheaper if we have a sparse tensor. Okay, so we have error analysis for this as well. And so this is going to take roughly the same form. It looks really complicated, but essentially what you can get from this is that the expected error is bounded by, and there should be, no, this is fine, okay, is bounded by the optimal error, which is the sum of truncated singular values in each mode, times this FP, which you'll notice is the same as that randomized factor that we've seen in all of the previous, and times this factor, which comes from the specific subset selection method that we're using. So in this case, we're using strong recombinant QR. If you used a different subset selection method, this part would change. But that one has nice theoretical guarantees, and so that's why we used that one. Okay, so real quickly, I just wanted to show some of the benefits of this on really large sparse data sets. So here I have two really large, really sparse multidimensional data that I got from FROST-T, or the Formidable Repository of Open Sparse Tensors and Tools, long to say. And essentially, I'm looking at the NEL2 data set and the NRUN data set with those word counts for emails. So here's just some statistics about these tensors. So NEL2 is 3-dimensional, NRUN's 4-dimensional, and it has these really large sizes. So it's very, very large, but the number of non-zeros compared to the size of the original tensor is very, very sparse. So the structure preserving algorithms can run on this data set on my laptop, which is cool, but the ones that we want to compare it to, so randomized STH, SVD, and things like that, can't handle it. It's too much. So in order to do a good comparison, we condense these tensors to run. But keep in mind that the structure preserving algorithms can run on things that are this large and this sparse, which is really nice. Okay, notice also for NRUN, even the 4-dimensional, if we just subsampled, it was still too sparse. So we ended up collapsing a mode to make it 3-dimensional as well. Okay, so here's some results for that. I'm looking at, for increasing target rank, we have the relative error and the runtime for our structure preserving on the left and our randomized STH SVD on the right. And you'll notice that our structure preserving is not doing as well error-wise compared to the randomized STH SVD for the same target rank, but the runtime is significantly less. So the idea that we have with this is, okay, say you want that 13% error, then let's just take a higher target rank of like 210, and we still have a reduction in time of about 5 times. So the structure preserving can work really, really well for even this large sparse data and get the error that you need. And that's the same for NRUN, and even I think it's even more dramatic with the NRUN data set, which is more sparse. Okay, takeaways from this section. Main idea is that if we preserve structure in the core tensor, we can compute with really large, really sparse data that is infeasible for standard decompositions, even randomized algorithms. So, and the way we did that is we combined randomized rangefinder with subset selection methods to extract entries from the core itself. And I showed that it was particularly useful for that sparse data. Okay, overall, using randomization for tensor decompositions can improve our efficiency, and we can get away with without losing too much accuracy, particularly when we exploit additional structure, such as the Kronecker structured matrix, such as parallel, and any of the sparse structure as well. Okay, so that is what I wanted to talk about. Happy to take any questions.